Okay, so let's start. So welcome to the EC Game Changer Seminar Series. It is the 104th series since we started during the Corona to serve the community even when EC was closed. Then we invented this seminar. It was so successful that we still continue with the seminar. Now it's once a month. Seminar actually started with the title as the Game Changer because we wanted to have seminars or missions which actually game changed the view in how we see the sky today. And I think talk today, it's again with the same aim how we started with this webinar series. It's a game changer, and it is about a polarimetry mission, X-ray mission. And I'm very happy to have here Yuri giving us this talk, since he's deeply involved in this mission since almost its beginning. So just about Yuri. Yuri is a professor for astronomy at the University of Turku in Finland. He got his university degree at the astronomy, he got his astronomy degree from the Leningrad State University and PhD in astronomy from the University of Helsinki. Then he worked previously at Stockholm and Uppsala universities in Sweden and at the University of Oulu in Finland before moving to Turkey to take up the directorship of Turola Observatory. His main research, he will tell us more during the talk. And of course, he's actually very broad, which is going beyond X-ray polarimetry. And about IXPE, he's leading the effort to uncover geometry of X-ray emission region in X-ray pulsars and non-magnetic neutron stars, as well as involved in discoveries of X-ray polarization from accreting black holes. So just some technical details before Yuri, you can start. So at the end of the seminar, you have the possibility to ask questions. There are almost 3 ways how you can ask your question. You raise your hand and then we will unmute you and you can ask the question directly. Be concise in asking questions and precise. Or you can write your question in the chat and then I will read the question to Yuri. So Yuri, thank you so much for accepting our invitation to give this seminar, and I will switch off my camera and leave you the floor.
Okay, good evening. I'm very glad to be here and to give this presentation. I hope you can hear and see me, because now I'm in the presentation what I can see on my presentation, but I cannot see anybody. So I hope that you will complain if there will be some problems with the presentations. So this, obviously from the title of the talk, you could figure out that this will be about X-ray polarimetry and the results that we obtained with the new satellite that is given the names here, Imaging X-ray Polarimetry Explorer, that was launched 2.5 years, slightly more than 2.5 years ago. So of course we would like to have images of black holes, neutron stars, compact objects in our galaxy, but unfortunately they're too small to be seen. For example, if you have supermassive black holes in our galaxy, in the Milky Way, or in nearby massive galaxies like M87, with the current radio interferometers, you can do the images of the hot gas accreting onto the black hole, as in this nice picture produced by Event Horizon Telescope. But unfortunately, for X-ray binaries in our galaxy, the sizes are much smaller. Angular sizes are 100,000 times smaller. And so the image, direct imaging at this currently is not possible. And it would be still nice to get another way to learn about the source geometry. And this way is provided by polarimetry. And polarimetry has been used, actually, of course, already for people claim for a long time, for 1,000 years. And already in the days of Vikings, there are claims that they have used this spot to analyze basically the scattered light even in the cloudy days, to get the direction of the traveling of the sea. And even bees use the polarized light to navigate to the nearest flowers. And in the astronomy, there are many ways to produce polarization. During this talk, I will talk about X-ray polarimetry, and the most important sources for producing polarization is electron scattering and synchrotron radiation. And depending on the type of source, one of the source normally either synchrotron or scattering, electron scattering is dominating. And synchrotron scattering, of course, tells you about the geometry of the magnetic field. And the electron scattering gives you about geometry of the scattering medium. So in basically all the compact sources that we can study, like in our galaxy, X-ray pulsars, black holes, and radio pulsars, pulsar nebula, in principle, you can get either one or the geometry of the magnetic field or the geometry of the scattering region. In radio infrared optical bands, polarimetry has been proved to be very important. But in X-rays, where you have non-thermal processes are important or some sphericity, we need the actual X-ray polarimetry just because many sources emit most of their radiation, the X-ray band. In the X-ray band, the problem was that there was no X-ray polarimeters until recently. The only polarization measurement that was done already back in 1970s was done with the Crab Nebula. That polarization degree of 19% was measured. This is the, of course, image from Chandra, but this was the instrument called also 8. And until recently, we were not able to do anything in the X-ray band, basically. And now you see the images of the Crab Nebula in different wave bands. And actually, the measurement of the magnetic field orientation of the regions which produce radio, infrared, optical photons. But in the X-rays, we had just basically one direction, so basically polarization direction. And we would like to learn, of course, more. Actually, I will not talk about Crab Nebula today, but the idea is the following, that actually most often X-rays tell you, in this kind of sources, tell you about where the electrons are accelerated, the region, the geometry there, and in other wave bands, probably the electrons are less energetic. So we cannot learn really about the acceleration process. So a little bit about the history. Actually, of course, starting from also 8, the polarimetry was, people tried to develop X-ray polarimetric facilities. It was proposed for Einstein Observatory, but then it was removed because normally, of course, you expect there will be some cost problems. When I was doing my PhD, there was a plan to launch Russian or Soviet spectrum and gamma mission in '93 with the number of X-ray polarimeters built, for example, by Bob Novik in Columbia University. And this mission, unfortunately, was never realized. It was cancelled in the end of the '90s because of the basically collapse of the Soviet Union and end of the there were financial problems. But now, of course, the Spectrum X Gamma mission with completely different instrument is flying and doing a good job. I was involved in the mission which is called GEMS, and that was a NASA mission selected in the 2009 or 8, I forgot. But it was cancelled because of the problems with the budget, also the potential problems that it was over the price proposed, like by 20-30%. And then there were polarimeters planned on board of other missions like Zeus, IXO. The good point is that these polarimeters got also finances, but the bad point that these missions were never realized. Because to study polarimetry, you need to have a lot of photons, much more observing time. For example, if you want to detect a source with Chandra, probably 3 photons would be enough. If you want to do spectroscopy, maybe thousands of photons would be good. But if you want to study polarization with the polarization degree of the order of 1%, you need millions of photons. And so that's basically the reason why until 2021, we had only one source detected. And of course, there's another reason that there was no actually any good detectors specifically designed to do polarimetry. So as I said, in 2021, IXPE was launched. This satellite, the PI was Martin Weisskopf. Now it's Phil Carrett because Martin retired just a year ago. And so here on the right, you have also a picture of him with the colleagues from Columbia University that made the first observations with the sounding rocket of the polarization in Crab Nebula. Okay, and so the IXPE was launched in December 9, 2021. It contains 3 telescopes with the 3 basically identical detectors. And it has the similar structure as New Star telescope with this matched, expandable matched. And here the only thing is that there's this, what you call the thing around the telescope, around the mirrors to protect from the stray light. And we have 3 detectors getting polarization. And the technique that you measure polarization of the incoming photons is based on photoelectric effect. The old days, people mostly use Thomson polarimetry, or there was Bragg crystal, but now there is this photoelectric effect. It turns out that this is a much more efficient way of measuring polarization of the incoming photons. So if you have polarization of the photon in the plane of this image, then the probability that the photoelectron will be injected is proportional to the, so it depends on the polarization direction, and it's proportional to the cosine square of this azimuthal angle. So you have sort of symmetric probability, but it's 0 probability perpendicular to this direction of polarization. And so then, obviously, if the photons are polarized, one can plot. So first, of course, you need to measure this direction of the photoelectron. For that, you need 2-dimensional detectors. So when the for the electron travels there in this device, which is basically gas detector, it leaves this like the footprint that you can image. And so basically each event is an image, which is, it means that it's actually very expensive in a sense to download all the data. But then from the image, one can try to determine the direction of the photoelectron. This is the red line here, original. And that gives the information about the polarization of the incoming photon. And then when if one would plot the distribution of this photoelectron as a function of the azimuthal angle, you will get this kind of double sine wave. And from the amplitude of this sine wave, one can measure the polarization degree. So actually, in the laboratory, one can calibrate that, and one can measure what's called the modulation factor. For 100% polarized source, what would be the amplitude of the sine wave? And for, of course, unpolarized source, there should be no modulations. Of course, it is typically small, but not very important for the sources that we will be talking about. So by now, IXPE, as I counted a couple of days ago, produced 72 papers that are published in all kinds of astronomical journals, including Science, Nature, which are not astronomical journals, but of course the general science journals, Nature, Astronomy, Astrophysical Journal, Letters, and so on. And here, as you see, there is basically all the papers that can be divided now in like 8 or 9 groups. And first 2 groups, this is the group which I'm responsible for, Accreting neutron stars. I'm the head of this topical working group. And we produced now 22 papers. And basically with the red here, with the blue, I try to make sort of mark those objects that I will try to talk about today. Okay, but also in addition to accreting neutron stars, we have magnetars, we have pulsars and pulsar nebula, supernova remnants, and stellar mass black holes that I will also try to cover today. Something about supermassive black holes that I will not talk about, and even one paper about gamma ray bursts. Okay, so let me start the story about from X-ray pulsars, because actually these are the objects that were predicted to be strongly polarized. And even before the mission was launched, at the discussion in the science working group, people said, okay, you, me, us, our group would get most of the polarized photons in the sense that among all other groups, because people were expecting these sources will be like 80% polarized almost. In the end, of course, it didn't turn. We were very optimistic. Unfortunately, the life was complicated. But anyway, so we were, already a long time ago, people discussed that actually studying X-ray polarimetry, you can learn about geometry of emitting region. Those days, like in 1988, there was models already proposed for accretion, actually before that, for accretion onto the strongly magnetized neutron star. For high accretion rate, you would have this kind of accretion column. For the low accretion rate, the matter will hit the neutron star surface. You'll have hot layer there on the surface. And change in the geometry of the emitting region would lead to the change of the pulse profile, because the emission pattern will change, and probably the change in the polarization. Okay, and because these are pulsars, so their magnetic field is misaligned from the rotational axis, you would, from the polarization, you would be able to measure geometry of the pulsar. What's the magnetic obliquity? What's the inclination of the pulsar, rotational axis to the line of sight, and position angle of this on the sky. So, and one of the proposals for our group was also that in principle, you would be able to measure free precession model for Hercules X1, which was one of the leading models for changes of Hercules X1 supraorbital variations. And the reason for why people thought that this X-ray pulsar was strongly polarized, because the opacity for electron scattering in a strong magnetic field is strongly dependent on polarization. There are these O mode and X mode photons. Basically, O modes in these oscillations in the plane made with the wave vector and the magnetic field, and X mode is perpendicular to that. And the O mode photon has almost Thomson cross section below the cyclotron resonance, and normally we are dealing in the IXPE band. This is below 10 keV. We are dealing with the region below cyclotron resonance, which is at tens of keVs. And the next modes, you would force the electron to oscillate perpendicular to the magnetic field. That's not easy. Then the opacities are very low. And this is basically reason why you expected that in the low opacity, you would be able to see deep in where the matter is hotter, and you would be able to have higher signal, and it should be strongly polarized. And then, of course, if the neutron star is rotating, one can predict actually how this polarization, at least angle, will depend on the geometry of the pulsar. And it turns out that because of the QED effect, that the polarization is adjusted when the photons are propagating along in the magnetosphere. That the polarization vector is adjusted to the geometry of the magnetic field, and it's detached at some large distances from the neutron star, where the magnetic field is basically a dipole, whatever happens on the surface. And therefore, you will be able to see just the rotation of the dipole field on the sky. And so then you will actually learn about the geometry of magnetic of the neutron star. So I hope you can see now the picture of the pulsar. This is basically, one can think that this is the beam is just the polarization angle. So basically the direction of the oscillation of the photons. And then if you observe from the side, then you just have small oscillation amplitude of polarization angle. But if you observe the source from the top, then this stick sort of rotates twice per each, because it's not a vector, but it's pseudo vector. It rotates twice, and you get sort of change of polarization angle by 360 degrees in one rotation. Okay, so already this rotating vector model sort of already discussed in the end of 60s in relation to the polarization of regular pulsars, and then by Misarash et al. In 98 in relation to the X-ray pulsars. So basically, what you would, if you are looking here along this O vector, and N and E, this is direction to the north and east, because of the magnetic field is misaligned from rotational axis, right? So the projection of this magnetic field on the sky will change with time. And this is the formula that sort of relates this position angle, polarization angle, with the position angle of the pulsar spin, and the magnetic obliquity, which is theta, and the phi, which is the pulsar phase, okay, and I is the inclination of the pulsar. So there is a formula, and if you have the data, then of course you can just apply this formula and try to get all these geometrical parameters. Just to get an idea of what you would expect, that for some different combinations of this inclination and the magnetic obliquity polarization angle would either be sinusoidal, which means that you're looking from the side of this pulsar, or there would be like this sawtooth dependence when you're looking from the top. And on the Stokes parameter plane, and of course polarization is described by Stokes parameters, and these are normalized Stokes parameters, which is basically Stokes parameters divided by the intensity of the flux. So then this you would expect it will be some kind of, in one case it would be like, I call it kidney pattern, just like ellipse-like, and in other cases you can have this red pattern, which is like the bretzel type behavior. We have observed now dozens of sources of X-ray pulsars and with various spin periods and various luminosities, and actually the first pulsar that we observed was Centaurus X3. This is the first pulsar that was discovered by Riccardo Giacconi in 1973. And what we learned there, what's on the left picture, that polarization angle basically makes sinusoidal variations. There are some outliers, but we can understand now because it depends on the energy range that you select the data. And another pulsar, which is XPRC, this is one of the closest, probably the closest X-ray pulsar known at 800 parsecs from us. It shows this kind of this sawtooth panel, this pattern, and this clearly it means that you are looking from on the source from the top, sort of, and then this. So we can actually determine the geometry of all these parameters can be determined. And in the Stokes parameter plane, in the first case, it's not clear what it is because of the errors, but it maybe looks like this ellipse line here. And in the second case, it's very nice example. It's really this bretzel. So it's perfectly consistent for X-ray pulse, XPRC. Perfectly consistent with the expectation of the rotating vector model. And actually, most of the data are consistent with that. Then we applied the same model to Hercules X1. And Hercules X1 has been observed now about 5 times. This is just in this year we have, I think, there's these observations of Hercules X1. So this is main on, and then there is short on, and there is again main on, short on. So there's different superorbital phases. And what we clearly see that, for example, polarization angle, the average one, is very different in different phases. So this is the red points. So for example, it's like 65 degrees. This is phase average. Also, phase average like 65 degrees in one case and like maybe, I don't know, 40 in another phase. So there's strong variations. Okay, and then when you do the pulse phase resolved spectropolarimeter, then you can actually see that polarization angle in one case it varies strongly, like by 30-40 degrees, but in another case it varies very little. So clearly pulsar geometry has changed between the different phases. You can apply the rotating vector model, and you get that there's strong change in the all geometrical parameters, which you can interpret as indication of precession of the neutron star. And then one can discuss whether this precession is the free precession of the neutron star or forced precession of the accretion disk, but actually probably it's a combination. The required deviations from the sphericity is at the level of 10 to minus 7. So for a 10-kilometer star, which means that this is like on the level of like millimeters. Okay, so basically it's a picture that you have because of the non-sphericity, you will have the precession of the neutron star here. That seems that the data are consistent with that. But the life is always not so easy as we would like it to see. Sometimes we observe complicated sources, and one of the brightest sources that we observed, this is the pulsar with this double name, the LS5 plus 4417. I call it went in the outburst. I think it's somewhere at the beginning of 23. IXPE observed it twice with an interval between the observations about 10 days. And what we saw is actually quite a dramatic change. The data, and I will show this is the right lower panel, this is the most important, the polarization angle as a function of phase. And what we saw was very dramatic change between the two observations. There were 10 days between, and the behavior of polarization angle changed absolutely dramatically. The data sort of consisted with the rotating vector model, but you get huge changes in all geometrical parameters, like in the inclination, in the magnetic ability, which first, I thought this is a very good example of precession, but then we thought that maybe it's a little bit too much. And we started to think about other possible explanations for this huge changes. And then what we did, we looked at the Stokes parameter plane. This is the two observations showed in two different colors. And what we saw that this pattern that they leave of the Stokes parameter plane, they're very almost identical. But what was striking that these two banana-like structures are on different sides of the region. So the black cross here is a 0, 0, yeah, so this is a region, and these two bananas are different sides. And then if one thinks, what is polarization angle on the Stokes parameter plane? This is the angle between the direction from the origin to the right and the direction towards the point. So for example, point, let's say 12 here, it will be 90 degrees, but you have to divide it by 2. Okay, so it's 45 degrees polarization angle. Okay, if you take number 1 point, it's just 0, but if you take the red point 1, it is almost 180 degrees divided by 2, so it's like 90 or 80 degrees. So there is a huge difference. But looking at this pattern, we realize that maybe there is more than a rotating vector model is operating here. So we realize that maybe there is a constant component that actually makes the shift of these bananas along in this plane. And we came to the idea that actually the Stokes parameters probably described by two components. One is phase independent, which like here is constant, right? And another is very also phase, which can be described by the rotating vector model. The data actually, you learn two things. You can first determine this constant component polarization property, and then you can determine the parameters of the rotating vector model. And this was a trick that you go from this data, which is on the left, right, to the data in the lower part. And they are just basically now what you see the lines are connecting the same kind of phase beams, and they are the same lines, which means the polarization angle is now the same. Okay, let me now stop sharing. I want to be sure that everything is fine. You can hear me, Maurizio, can you confirm?
It's fine. I can hear you. Sometimes it happened that we could not. You disappearing for 1 second, but only a few times. But we can.
Okay, good. I think this is probably my internet connection. It's okay, might work. Okay, let me then continue, because I wanted to be sure that at least I was talking to actually somebody. Okay, so now this transformation from this very different polarization angle dependence to the similar or almost identical, which is amazing, I think. This is just adding a few more parameters, you transform this to the same dependence, and it means that you can describe the data with the same rotating vector model. And of course, at the same time, we can actually say that, okay, what is this component, this constant component? We can measure polarization angle, so of this component, which is about 70 degrees. We can measure polarized flux. This is basically how much in average units of average flux of the pulsar this component contains is about 3%. So, for example, if it can be 100% polarized component producing 3% of flux of the average flux, okay? Or it can be 30% polarized component producing 10% of the flux, all right? But we cannot distinguish between these two possibilities. But what it is, and the only explanation that we thought that it should be phase independent, maybe it's some scattering in the wind, because these are very strongly accreting sources. If you have equatorial wind, and you have X-ray source in the center, and you have scattering of this radiation in the plane, sort of, and you can get this polarization can be easily 30% polarized, and there is no problem for 10% of radiation would be scattered, and so that's a reasonable explanation. We cannot prove that, but it doesn't, it's not contradicting anything. Then what actually we observed, we tried to get the orientation of the binary system looking at the optical polarization, because this source is a B star, so it has the accretion disk around B star. And the optical polarimetry tells you that the orientation of some symmetry axis in this system is also about 70 degrees. So it's actually consistent with the polarization angle that we measure in X-rays with the constant component, which sort of tells you that probably this interpretation of scattering and the accretion disk wind makes sense. But of course, now we have to check that this complication because of the two components at least that produce a polarized signal is actually doesn't affect our interpretation, for example, of Hercules X1 free precession, but that's something to do in the future. The second type of object that I wanted to mention, these are non-magnetic accreting neutron stars. Okay, so these are accreting neutron stars which are not pulsars, so they don't have strong enough magnetic field. They are they depend on the accretion rate. They could have a sort of a standard accretion disrupted, and maybe there is a hot flow there. It can be in the hot state. At high accretion rate system, you have disk interacting with the neutron star directly, so there is no magnetosphere, and there is a boundary or spreading layer. Then when this matter tries to spread over the neutron star surface. Okay, so basically now we have also 10 sources observed. You would expect there are two components, at least in the spectrum, one associated with the disk, accretion disk, another associated with the boundary or spreading layer. The disk is bigger than the spreading layer, so therefore it's cooler. So this is the accretion disk, this BB model. And then the boundary layer is hotter, obviously. So this is the component at high energies. You have the spectrum can be decomposed into those two components. Okay, and we know from variability properties that actually the high energy component is variable, much stronger. So there are these quasi-periodic oscillations, the kilohertz observed in this in this component. So this is clearly something related to probably the surface of the neutron star. But the reason why this quasi-periodic oscillations are happening, that's we are not going to discuss. There are many models for that. The first source that we observed was Cygnus X2 and another Cygnus source. Right? So we have the three sources that actually are mentioned today. But Cygnus X2, we observed actually quite slow polarization, less than 2%, polarization angle 140 degrees. Okay, and then when we write in the paper, I found the very old paper from 1980, observation from also 8. And looking at this paper, the also 8 team, they didn't claim that they have a detection because the signal was like less than 3 sigma. Here's the polarization degree was 5% plus minus 1.8, less than 3 sigma. So it's sort of non-detection. And therefore people say that, okay, Crab is the only one that also it has this detected. But what's amazing, that polarization angle is identical to what we measure now with IXPE. And in the meantime, there were radio observations, and the radio jet was detected at the position angle of 141 degrees. And so we have now 3 numbers which are coinciding. There is no error on this radio jet position angle. So I don't find this coincidence like just coincidence. I think this tells you something. And basically tells you that most of the polarization is along the jet. How do you make it? And of course, if you have emission from the surface of the neutron star, which is like a belt around the neutron star, so which has the major geometry along the symmetry axis, along the jet, which you would think is going perpendicular to the accretion disk. So then this is easy to explain this behavior, right? So you can have the polarization produced in the spreading layer. Maybe 2% actually turns out to be quite large. But on the other hand, you can also some of this radiation can be reflected from the accretion disk because the accretion disk works like a mirror, and it can be easily polarized up to a few percent level, 6% on average even could be. Or again, as I mentioned, there could be scattering in the wind. All these 3 models probably would be consistent with the data. The spreading layer cannot produce 5% polarization, that's we know, but 2 other models can. So, for example, old papers by Lapidus and Sune from 1985, they computed radiation scattered from the accretion disk, and then they get easily like 6% polarization degree, which is more than actually even we need. But of course, the result will depend on the height of the spreading layer. And the scattering in the wind, this is the simple formula that mu is the cosine of the inclination. Basically, you can get up to 33% polarization, so which is also easier. Okay. Okay, we thought that we understand something, but then one of the sources that I wanted to mention, this is Circon 61. This is a very interesting source. It is the youngest X-ray binary in our galaxy, at least that we know of. It has a supernova remnant around it, so it's estimated the age estimated to be just 5,000 years. So it has a very elliptical orbit. Period is quite large, about 17 days. We observed like a couple of times IXPE with the interval also like a big bit between them. And what was so the spectrum actually didn't change very much. It also had these two components. There's no big change in the hardness ratio, just the flux was changing. But the polarization was very different. If you observe two times observation between them, they're like 50 degrees, the polarization angle varies. So there is a big change in the polarization angle. And it's clearly inconsistent with the position angle of the jet. And this is first thing that we clearly don't understand what's happening. There are the same spectrum basically, but completely different polarization angle, not consistent with even 5 sigma, right? So, and it's nothing to do with the jet, which is also measured in this system. And we try to understand what's happening, that we invented this kind of model that you have maybe, because it's a young system, maybe the neutron star is rotating on the side. So there is misalignment between the rotation axis of the neutron star and the orbital axis. So you can have dependent accretion rate. Maybe you can have different situation when you have this kind of spreading layer, which is on the surface of the neutron star. It's rotate together with the neutron star. At some other time, you can have the emission coming from the boundary layer when actually neutrons sort of high accretion rate, the accretion disk goes all the way in. And maybe even the neutron star is precescent. So actually, there is no any good model for that. So it's an interesting exercise for people who cannot do simulations of the accretion to the neutron stars. What's the right geometry? Is there anything like that can happen? But we actually don't know. But there is something clearly changed in the system that we don't really understand. And the most striking example is the paper. Now we have like 3 papers about this source, but this is from the first paper of my student Anna Bobrikova. That's where this is the also similar system, GX13+1, that is accreting like luminosity is half the Eddington, also very large orbit, like 24.5 days. We observed at high inclination, and what we noticed that during a couple of days, the polarization angle changed by 70 degrees. Okay, there was just this line, so it's clearly a huge change between -40 and +20, maybe more, right? So it's and this is just something that we really don't understand. We have a couple of more observations, which we get this on QU Stokes parameter plane points somewhere in the same place, but not so strong variations of the polarization angle. And again, what is happening there is the evidence for the misalignment of the neutron star orbital spin. We don't understand what is happening. We can speculate, but we don't have any good proof. So actually, we need something, some model, some new ideas what's happening there. Okay, let me now switch to stellar mass black holes. I will have a couple of examples for this source. For the source, maybe Cygnus X1 is the most famous one, right? This is from 1965. People discussing this is the first black hole candidate. We have Cygnus X1 is observed in different states, hard state and soft state. And one of the questions that people ask in the hot state, for example, what's the geometry of this hot X-ray emitting region, whether it's a hot flow or there is some corona above the disk, or maybe there are some flares, or there's a lamppost even people discuss, or maybe the base of the jet. And so actually polarization is dependent now, it depends on the geometry of the source. And everybody agrees probably that the spectrum in the hot state is produced by multiple Compton scattering, so it's called thermal comptonization. But the polarization should depend on the geometry of the source. So it should tell you whether the source is elongated vertically or horizontally in this picture. Okay, and then the observations, which are now 2 years old, we detected the polarization with very high significance, and polarization angle, okay, -21 degree, is perfectly consistent with the direction of the radio jet. So the radio jet here is this radio contours, and the position of the polarization angle is this orange line. And this is perfectly consistent. Actually, we actually measured optical polarization in the same direction. So there are some systems, some symmetry axis clearly that tells you about this fixed geometry. And then the question is, what's the geometry of the emission region? And the only explanation basically is that the photons that are Comptonized should be produced scattered in the region which are perpendicular to the jet. And the reason for that is that when the photons scattered many times and they then finally scattered towards observer, which are, let's say, a little bit on the side, right? The polarization, the electric vector acceleration will be perpendicular to the slab, to this region elongation. And in that case, it will be parallel to the jet. So you need to have the region which is perpendicular to the jet and quite flat. So it can't be anything spherical because the polarization will be just perfectly zero. It cannot be lamppost. It cannot be base of the jet, let's say, because if you have elongation in the vertical direction, then the polarization will be perpendicular to the jet. And this is not what we see. Okay. So we learned something about geometry there. So it's probably the correct geometry. Then I will say it's probably some hot flow of the corona. But there are some arguments why it can't be corona because you actually don't see the accretion disk here. But so maybe the hot flow model is the correct one. That's actually quite flat. It can be semi-spherical. The last source that I want to talk is Cygnus X3. This is really amazing source. This is again another Cygnus source. Okay, even also 8 had the paper in 1980 about Cygnus sources, X-ray polarization of Cygnus sources. And here again, we have now, of course, Cygnus sources that are one of the brightest ones on the sky, among the brightest ones. So this was also discovered in the 60s, Giaconi paper from 67. It has no optical counterparts. There is huge orbital variations in X-rays, infrared, gamma rays everywhere. It's a very short orbital period, less than 5 days. It contains Wolf-Rayet star with a strong wind. There are models trying to explain all this infrared X-ray data. You can measure inclination about 30 degrees. So these are interesting sources that that can produce sort of in the future and double degenerate star with this kind of black hole neutron star systems, similar to what are nowadays detectors as gravitational wave events. It has a jet in the north-south direction, so position angle 0. And what's interesting that I will discuss only one state, which is sort of hot state. People are discussing also what is the, for example, origin of this hot state. There is a peak of the emission, not at 100 keV as we see in Cygnus X1. It's at 20 keV. And in the papers by Andrzej Dziarski and his collaborators, they tried to fit this data with 3 different models. Some soft spectrum reflected from somewhere, from cold material. There is a harder spectrum, also absorbed in the Wolf-Rayet wind, and so on. And I think this is the 3rd model, is the reflection spectrum. So you can have some different models. And the question is how you can tell them apart. Turns out the polarization actually does tell you. Now we have a number of observations of Cygnus X3, 2 in the hot state, and one is sort of, there is another state, a couple of another states. But let us discuss these points which are blue one, polarization degree that we measured as a function of energy. It was like more than 20%. And this is really, even in Cygnus X1, when we measure polarization at 4%, we were shocked because that's a little bit too much. How you make 4% polarization is not so easy. But here it was 20%. This is something that was really interesting. And the polarization angle now here, it's 90 degrees. As you remember, the jet is at 0 degree. So it's 90 degrees away from the, it's perpendicular to the jet. So it's obviously completely different geometry than what you imagined in the Cygnus X1. But if you look at the spectrum carefully, if it is indeed reflection, there is a strong iron line. Of course, in iron line, you'd expect depolarization because it's unpolarized, it's fluorescent line. But the continuum, if it's reflection really, it should be strongly polarized because if you reflect, it's like a mirror, like Thomson scattering, it should be polarized. 20% polarization, it's actually not easy to make, but you can make a model. And the only way to make that working, right, because the interesting thing is polarization doesn't depend on the energy, except this iron line feature, that is depolarization. But otherwise, it's the constant with energy. And if it's constant with energy, it means that you have basically single scattering, single reflection. Okay, so we can make a model, and you don't see the central source because it will be then much less polarized. So the only model that we sort of invented is like you have a central source which you cannot see. This is, let's say, an accretion disk. Then you have, if you put a wall, like a conical wind of the wall, that with it's empty inside and it's optically thick outside, the photons from the central source can be reflected towards you from this wall of this wind. And then, of course, they are strongly polarized. And easier calculation give you that they should be polarized perpendicular to the symmetry axis. And varying the parameters of this opening angle of the cone and inclination, which we think it's about 30 degrees, not we, but I mean, there are other papers claiming that, you can actually tell that the opening angle of this cone is about just 10 degrees. So because polarization degree, scatter, it should be about 25%, and this means that there's this plane inclination versus opening angle of the cone, and you get 25 degrees, but 25% polarization is about 10%, 10 degrees opening angle. So this is amazing. It means that actually you don't see the central source, right? And all you see in the experiment is just reflection. And it means that most of the radiation actually doesn't go towards the observer, it goes somewhere else, or it's along this axis. So it's collimated by this wall. Right. So, and one of the main models for ultraluminous X-ray sources is that you have super Eddington accretion, you have a strong radiation, like the wind that is pushed by radiation pressure, and because of the angular momentum conservation, you would have some matter, no matter along the axis, but there is a wind which is slowly expanding, conical-like structure, and this means that, and of course, this wind collimates radiation away from you towards the axis, right? So if you are lucky, you will see the source very bright if you observe it along the axis. So Cygnus X3 is probably this kind of ULX, but for the observer along the axis, we are not lucky enough. We observe it from the side, a little bit sideways, and so it's a hidden ULX. Okay, that's the paper just recently published in Nature Astronomy. You can estimate also what's the intrinsic luminosity of the source and so on. Okay, so I think I came to conclusions that IXPE has opened new window to the universe. This is the X-ray polarimetry window now. And there are many discoveries that we made and many things that we don't understand. We thought that we will understand with X-ray polarimetry, but some questions, new questions, of course, appear. We learned about geometry of X-ray pulsars, like we probably learned also, hopefully, to learn about precession in physics 1. We found evidence for misalignment in non-magnetic neutron stars. We have an accreting black holes. We know that in the hot state, there are emission regions perpendicular to the jet, and the lamppost jets are ejected. Even Cygnus X3 is probably a super Eddington source. And just to mention the IXPE calibration, and the two leaders of that, Martin Weisskopf and Paolo Safita, got this year Bruno Rossi Prize for development of the Imaging X-ray Polarimetry Explorer and novel measurements that advance our understanding of particle acceleration emission from astrophysical shocks. Black holes are neutron stars. And this is the picture that I think was made a number of years ago, that people predicted, okay, what would be the sky map of X-ray polarized sources in a few years' time? Because 3 years ago, basically, we had one source, Crab Nebula. Now we have many sources, actually. And this was our imagination, what we could observe also. But actually, IXPE has observed most of the sources. We have molecular clouds. There are papers about Sagittarius A cloud, very strong 33% polarization that tells you about activity of our central supermassive black hole in our galaxy. We observed pulsars and pulsar wind nebulas, the radio galaxies, NA, supernova remnant, at least Tycho and Cassie, and there are some other nice supernova remnants, X-ray binaries, many of them, right? So mentioned wind-fed X-ray binaries, Vila pulsar, Vila X-ray pulsar, also we observed, for example, another source in Cygnus X1, Cygnus X3. And we observe magnetars, blazars, Seyfert galaxies, pulsars, of course, and pulsar nebula. We haven't observed galaxy clusters because they are in X-rays, this is just probably thermal Bremsstrahlung, which is not, it's probably would be good calibration source with zero polarization, but we haven't observed it yet, and probably we will not. Thank you very much.
Thank you so much, Yuri, for this beautiful presentation and showing once more how emission can answer questions, but open again new questions that we don't understand. And of course, congratulations to you and all the teams for IXPE and also for this excellent prize the mission received. So questions, there are again different ways to ask questions. You can raise your hand and you will be unmuted and ask the question directly to Yuri, or you can write down the question and I will read the question to all of you. So please.
Because I cannot see the faces. For some reason, I cannot get
I think the cameras always, you can only hear them if someone raises the hand.
Okay.
Yeah. So we can unmute the participant for questions, or they can write the question, of course, in the chat. So questions.
Maybe you can unmute everybody, then they will have easier time asking questions.
I don't know if this is possible. So I have a question. So what is in European the most excited, unexpected results from this first measurements?
No, we have like 70 papers, yeah, but for me, of course, I mean, probably the most unexpected was polarization from Cygnus X-ray. Even it's not in my group, this is a Accreting black hole, people think, yeah. I think nobody expected that it will be 25% polarized. So this is something that, you know, this is, I don't think, and it is really very interesting. If our interpretation is correct, that it's ULX, then it's really exciting. Of course, on X-ray pulsars, now we learn about geometry, but this is something that we expected. We didn't expect that it will be so little polarized because the polarization degree that we measure is maybe 20%, not 80. But okay, that's we can live with that. But but at least I think the black hole was, and for example, I didn't mention there are exciting results from Vela pulsar with nebula, which is 70% polarization measured. So it's basically a maximum you can expect for its synchrotron. So it's clearly a very ordered magnetic field there. And in blazers also there are interesting results. But I think in every field that we just touched upon, there are some new exciting results. So it's some things we expected, you know, understand, but some things are not expected or not understood. Yeah.
Okay. So we have a question from Nuno Pereira. So what is known about the formation of stars and planetary system using X polarimetry?
Oh, no, yeah, unfortunately, these are the sources that are quite weak in X-rays. So that, as I mentioned, in order to do X-ray polarimetry, we need bright sources. The weakest sources that we have studied in X-rays, these are called Seyfert galaxies, and they're like 10 millicrabs. Okay, so there's 100 times weaker than the crab, which is one of the brightest sources on the sky. And then to get even one measurement average in all energies, you need 1 million seconds. Okay, so basically you go for a couple of week observation or more. We observed NGC 1068. Fortunately, this is a Seyfert 2 galaxy, which is like also a million seconds on that. It had like 20-some% polarization. So this is very happy that okay, sometimes they are very strongly polarized and we are lucky then to measure. But planetary system formation of like star formation regions, they're just too weak to do. This is, we cannot say much. There are many sources, weaker sources that we cannot observe. We haven't observed any white dwarfs even, for example. Like there are Accreting white dwarfs, they're just, we can sit on them maybe next time somebody can propose for GEO program, guest observer program, but you need 1 million seconds to get reasonable signal, which would be interesting. But you know, and the stars, one can see them active stars in Chandra, but you know they're much too weak to do X-ray polarimetry, unfortunately.
So please ask your questions. You can still raise your hand and then we will unmute you. So how many people, when you publish a paper, are, you know, then taking these new results and try to understand and also model different different models on what is new and unexpected.
Yeah, there's a question about
there is a
magnetic
new
field of black
question.
holes.
Yeah.
I can read. Yeah, so unfortunately, it's not easy to say because most of the radiation that you see in X-rays from accreting black holes are produced by Thomson electron scattering, thermal quantization or non-thermal quantization. But so basically, what you learn from X-ray polarimetry about the geometry of the X-ray emitting region. Then you can interpret some of the data as, for example, the seed photons, the seed photons that are upscattered. You can say, okay, they're produced by synchrotron radiation, but they're not very sensitive to the magnetic fields. How big is the magnetic field there? Because once the photon come from optical, let's say, to the X-ray band, they have scattered 20 times, and so you cannot say much about what was the conditions of when they were produced, what's the magnetic field, what's even magnetic field geometry. Unfortunately, not all of the questions we can answer.
So there is someone raising a hand. Please ask your question.
As there's nobody asking questions, maybe we can make a short excursion to the Vela supernova remnant pulsar wind nebula. Do you know?
Yeah, I even have some slides. I can show you if you want. If you have time, I can. I have another 100 slides. Yeah, so. But I just had the selection of slides actually. That's. Can you see now? Yeah. This is Seyfried galaxies. If you want, I can tell about them. This is Sagittarius A star. Vela. Yeah, this is here. Yeah, this is I think the image not obvious from IXPE, but this is the image from IXPE. And what you see there, pulsar nebula, these are this magnetic field geometry. And polarization degree on average is 45%. On average, all over the whole. But in places, here somewhere it's 70% polarized. Of course, the resolution of IXPE is not of course, not Chandra. This is like 30 arc-second resolution. So it's making these images of the compact sources not trivial, but you see this is 63% polarization of the size of this box. So some of these are bigger. So this is very ordered, like toroidal-like structures of the magnetic field. So there is not much turbulent magnetic field there. And yeah, so this is the other sources.
Okay, many thanks. But I mean, how does this bring us forward in understanding?
I think at least it tells you about the geometry of the magnetic field, because some of in this pulsar nebula people claim at least that you have diffusive shock acceleration. You need to have maybe there at the shock you would have turbulent magnetic field or something. This is not what you see easily. This is clearly very ordered magnetic field. So I'm not specialist in pulsar nebula, but what people tell me is that it's clearly not so easy to interpret this. For example, how to accelerate particles once you have such nicely ordered magnetic field. So this is
okay, many thanks.
Nicola Bocciantini would tell you more if you want to ask him. He's the leader of this group that work on pulsar nebula.
There is one more question. Also, I faced a problem to solve radiative transfer equation with polarization. Okay, this is something more private. I think everybody can write an email to Yuri. So normally this game changer seminar lasts 1 hour. So if there is one last urgent question, please raise your hand or write it down in the chat. Otherwise, I invite all of you to subscribe to our EC newsletter. Then you will be informed about the new game changer seminars. And yeah, so Yuri, thank you once more for accepting our invitation. And thank you to all the people listening to this seminar. So
thank you, Mauricio, and all the speakers, all the listeners. Thank you. It was very nice to be here. Thank you.
Bye. Bye. Bye.
Bye. Bye.